In this lesson, we are going to learn about the rate of chemical reaction. Well, first of all, think of the term rate. That's talking about how fast or how slow the chemical reaction occurs. Now we have something called the rate law. Basically, it's a law that describes the chemical reaction in terms of the rate. Well, this law is expressed in terms of the concentration of the reactant. Here we have this general equation of a chemical reaction. Of course, we have the coefficient and then the chemical, coefficient, then the chemical. And we have A plus B plus C equal to D. And these are reactants, where this reactant combine together to make the product. But in terms of the rate law, it's talking about the reactants only. Basically, if you look at this right here, we have the rate of reaction, or the rate law of this chemical reactions equal to K times the concentration of A times concentration of B times concentration of C, and they all to the power X, Y, Z. Well, that X is relative to A, but look at this, why are we using different variables instead of A, B, C? That is because this X right here, X does not equal to A, Y does not equal to B, Z does not equal to C, because these are not your coefficient number. So be careful with that. This has to be a number that we figured out later. I'll show you how to do that. But keep in mind, they are not your coefficient number. There are three types of rate law. The first one is zero order, first order, and then the second order. And each of them is defined by a specific rate law. For the zero order, is equal to K. For the first order is equal to K times the concentration of A. What is the difference between the two? Well, in this case, for the zero order is independent of the concentration. That tells you that the rate of this reaction does not depend on the concentration. Where the first order, you have K times A, that tells you that the rate of this is dependent on the concentration, or the initial concentration of the chemical reaction, where the second order is dependent on the square root of the concentration. So keep that in mind. Now, because of the differences in terms of the rate law, the unit of K is also different as well. But we have this equation that allows us to solve for these right here. And that basically, you take your M, and M, of course, is the unit of molarity for concentration. You take 1 minus the number of the order. So in this case, if we look at that zero order, what's 1 minus 0? Will give you 1. And that's the reason why we have 1 right there. That's because 1 minus 0. Where over here, if we have the first order, for M, 1 minus 1 gave us 0. And that's the reason why we don't have M there. Then over here, we have 1 minus 2, that gives you a negative 1. And that's the reason why we have a minus 1 there. And if we look at all of them, what do they have in common? They always multiply by s to the minus 1. And of course, s to the minus 1 is actually equal to 1 over s, okay? Which is your second. This is your second right here. That is actually second in time, okay? So be careful with that. And they all have time 1 to the minus. And they all have s times to the minus 1, okay? So that's the pattern for the unit of the rate constant. In addition, you also have to realize that different order of rate law will represent by different graph. And they always represent in terms of the linear equation. And if you have the linear equation, it's always expressed in terms of y equal to mx plus b. That mx right there, that m is your slope, isn't it? And this y right here is your y-axis. And of course this x right there, of course, is going to be your x-axis. Now if we were to compare them in terms of the different order, you have to memorize this. But the beautiful part is that on the back side of your periodic table is actually give you the first order, and it's also give you the second order. Look at that. And then for the zero order, you have to memorize that, of course. And this is the half-life of the first order, and we talk about this later. But it is given to you on the back side of your periodic table, okay? The first order and the second order. How can we use this information to solve for that? Well, look at this. If you realize if k, notice all of them has k, that is your slope. So this must be, that t right there must be your x. So all we have to do is to bring that over. So we have this. Let me rewrite this down here for the first order, okay? So what we have here is, of course, going to be natural log of at equal to negative kt plus natural log of concentration of A as 0. That 0 right there happens to be at 0 second, okay, or the initial of your concentration. Where t, notice we don't use the term f, that's because it's final, where t is happening at any time. So you can solve this using at any t. Well, in this case, if we look at this in terms of graph y, this is your y-axis, and this is your x-axis. So we can look at the first order right here, right there. If this is a negative slope, I just have a negative slope, a linear equation, that's what it is, this graph right here. See this right here, this equation is a linear equation. So this has to be a negative slope. And the tricky part is that the axis right here, see this has to be your y, so this has to be natural log of A. What is your x-axis going to be? Of course, your t, which is your time in second or minute, it doesn't really matter, okay? But that's how you're able to use this or that to figure out the graph. Well, let's look at second order. We have the second order. Let me write that right here, okay? For the second order, we have 1 over the concentration of that specific time minus 1 over the concentration of 0 equal to kt. Notice how k is positive. That tells you the slope is positive. So I can say that it is a positive slope. If I were to bring this over here, okay, why am I bringing the 0 over instead of the t? That is because, look at this. If you look at this graph, you are initially at time of t, right there, at time of 0, you have specific concentration. That's where your slope line, that's where your line intersects with your y-axis. And that's the reason why we bring that over there. If that's the case, then your axis in this case must be 1 over the concentration, and this is your time. Is that easy? And then if we look at the 0 order right here, of course the same thing right there. You have a negative slope, but the 0 order doesn't give to us on the back side of the periodic table. So you have to realize this is first, second. Think about it. In this case, we have negative slope. What is your y-axis going to be? Of course, it's just be your A, and this would be your time. And that's all it is. Before we move on to the next topic, one thing you have to realize that radioactivity is actually an example of the first order, okay? And because it's the first order, we have to realize that the half-life of radioactivity K is equal to 0.693 divided by K, which is your rate constant. And what happened in the test is that I will give you K, or you have to solve for K in order to solve for T. But that is given to you on the back side of your periodic table right there. So remember, this is your first order, not your second order. So anytime it's dealing with half-life relating to this kinetic, we are talking about the half-life of the first order, okay? Then we have more information about the reaction rate in terms of K. Well, and if we look at the calculator, look at E. E is relative to the natural log. So basically, if we look at that right there, that tells you this must have an effect on this values right there, okay? So if we look at this values, is actually equal to negative EA divided by RT. When you take E to the negative number, and when that number is smaller than 1, okay, since we're talking about a fraction here, this part right there is always relative to 1. It turned out that you will have a larger number. Now this is all relative to that smaller number relative to 1. Why is it becoming a larger number? But before we can actually look at this, we need to realize that e to the negative 1 is equal to a specific number, so that way we can compare them to. So e to the negative 1 is equal to 0.37, where if I were to take e to a smaller number, let's do that. So again, the smaller number is relative to that number. We're ignoring the negative sign for now, okay? So let's e to the negative 0.5. That's where I want to focus on. Okay, 0.5. So e to the negative 0.5. Look what happened to the values. It's actually equal to 0.61. Where if I do the opposite, if I take e to the negative of a larger number than 1, it would do the opposite effects, which will give you a smaller number. Okay, so in this case, it's equal to 0.22. Okay, so keep that in mind, and that's extremely important in mathematical term. That is because if you increase your activation energy, okay, let's look at this graph where it describes activation energy, and of course activation energy is the minimum energy for you to pass this transition state going from your reactants right here to make your product. If you don't have enough activation energy to go over that hill, you will stay on this side of the hill forever. So that's extremely important, because if you're increasing the activation energy, what happened to your reaction rate? Of course, it's going to get slower and slower. So if I were to increasing this, the reaction K, the rate your K will be getting smaller and smaller. And in mathematical term, it's proven that right there. If you're increasing these values, right, the fraction will be larger than 1. The fraction will be larger than 1, therefore it will give you a smaller number in terms of K. So that's the logic in terms of mathematical. Where we have another variable right here, T. Let's talk about T. T is your temperature. If you're increasing the temperature, you're increasing the collision of the molecules. Of course, your reaction rate will be faster. But in terms of K, you have to realize that K is the rate. So let's look at mathematical term. If we will look at T, if I were to increase T, that means more collision, okay, more collision, what happens to the fraction? That fraction will be less than 1, okay? You keep dividing by a larger number, you have less than 1, and look at the values. Of course, less than 1 will give you a larger number, and that in the end will give you a larger K. So know the mathematical relationship between it and that right there. And lastly, we have the term that's being introduced in this graph as well. It's called the term catalyzed. In this case, the word uncatalyzed versus catalyzed. What does that mean? This is basically using catalysts. And look what happened when we use a catalyst. It's actually lower the activation energy. So using a catalyst to lower activation energy, which is your EA. So that's a function of a catalyst. It only affects the activation energy. It does not affect your delta H. Nope, it does not affect your delta G. Because the word delta is relative to final condition minus the initial condition. Okay, so keep that in mind. Catalyst does not affect your delta G or delta H. It only the lower the activation energy, which in the process, it will speed up the chemical process. It will increase your K, which is your reaction rate. And another important concept that you have to realize about reaction rate is that most reactions happen in a process of a series of reactions. Basically, if we look at this reaction right here, that in order to make that product, you actually use multiple steps. And each step has its own specific rate. Some are slow and some are fast. But in terms of slow and fast, if we were to describe the rate of this overall reaction, what it's gonna be described by, and of course, it has to be described by the slowest chemical reaction process. And that, here we have the term RSD. RSD is basically the rate determined step, and that is based on the slowest steps. So in your series reaction, it will tell you it's slow or fast. If that's the case, the rate law will be based on the slowest steps. So the rate law for this will be what? It will be relative to the reactant. So we have NO2, and that would be F2. But we don't have the data to tell us a number of this exponent. So sometime, well, to make an estimation, we can actually use the coefficient. So if I were to put a coefficient 2 right there, that number would be 2. But this is estimated, if that makes sense. It's not the actual values. I'll talk about solving the actual values later. But that's the ideas of slow and fast. Now, in addition to that, we also have the term intermediates and catalysts. Well, we talked about catalysts already. A catalyst is basically used at the beginning of the reaction, basically introduced as reactants in one of the steps. But in the end of the process, it still exists as a product. So it shows up in the beginning of the reaction, but it's also present at the end of the reaction. So let's look at this together and talk about a catalyst. Then we also have the term intermediates. Well, what are intermediates? Think of the word intermediates. So this is the chemical that is being produced in the process, but it is later on used up in the process. So the key word is produced in the product, produced as a product, and used up in the process. Now let's do an example based on this problem. So first of all, we had to combine this together to determine if there is an intermediate or a catalyst happen in this process. So the process is pretty easy. You combine your reactant and then you combine your product together. So in this case, we have that right there. So we have 2NO2 plus F2 right there. 2NO2 because there's two of them in both steps, and then you plus your F right there. And on the product side, we have that, so that combined together. So NO2F plus your F right there. And if we look at this, look what happened to the F. It happened on both sides, so we can cancel that out, right? Then what about the F2? Nothing we can do. And then your NO2 cannot cancel out with anything. The same thing with that one. And the same thing with this one. So in this case, do we have a catalyst or an intermediate? Or an intermediate? Well, the F is being canceled out. But look at the chemical F. It is happen to be in the product side. So that tells you this cannot be your catalyst. In order to be a catalyst, it has to be on the reaction side at the beginning. So F is your intermediate. Where in this case, do we have a catalyst? No, because there's nothing else, right? So there would be no catalyst. Now let's look at another example. In this case, we haven't given ourselves our overall reaction, and we haven't determined in terms of slow or fast. So what if I make this to be slow, and what if I make this to be fast? It doesn't matter. Just use this to understand the RSD, which is the rate determined steps. So if this is the rate determining steps right there, right? So your rate for this right here, your rate law would equal to that right there, which is O3 times Cl. And of course, if there's nothing there, that tells you it has to be 1. So what's the total order will be? So what is the total order of this reaction law going to be? Of course, 1 plus 1 gives you 2. So that's the total reaction rate law in terms of the order. And over here, if this would be just 1, of course that would be the total as well. If this would be a 2, that would be a 3 reaction rate law order. Okay. Now let's get back to this. Since it doesn't give us the overall reaction, we can actually combine it together to figure this out. Because we did the same thing over here, right? Notice how this and this is the same thing as that. So let's combine them together. I'm going to rewrite this over here. So we have, let's group this together. So we have the reactant over here, which is O3 plus Cl plus ClO plus that. So we have our reactant, then we combine our product. And what do we notice? The Cl on both sides, so we cancel that out. We also notice, what else? This gets canceled. So if we look at this one, if we look at this 2, How do we know if it's an intermediate rather than a catalyst? Well, let's look at Cl. Cl is right here. So it's being introduced as a reactant, okay? So that's a good possible chance it's going to be a catalyst. And it's also, again, present in the product. So that tells you that Cl must be a catalyst. Where let's look at ClO, okay? Well, in this case, it is happening to be produced in a product side. Okay, so it's a product, so it's being produced. Where in the process being consumed or being used up as a reactant, so that tells you that ClO must be your intermediate. And that's the key difference between a catalyst and intermediate.